Hello, class. Mathematical modeling is the use of mathematics to help make sense of the world in which we live and to also answer other curiosities. The first task. A company sells phones for $150 each. The cost to make one phone is $30. Also, there is a fixed monthly cost of $20,000 no matter how many phones are made. Let X be the number of hundreds of phones made and sold in a month. Do the following. First of all, let's make sure we understand what this is saying. Let X be the number of hundreds of phones made and sold in a month. So if X is 3, that would mean that we really have 300 phones. So whatever X is, you have to multiply it by 100 to get the actual number of phones. Express the monthly revenue, cost, and profit as functions of X. Let's begin with monthly revenue. We'll use capital R of X for the revenue as a function of X. It's going to be the price per phone, which is $150 per phone, so per PH, I'll write, and then multiply it by the number of phones, which is 100 times X, phones. So the phone units will cancel, giving us dollar units, and 150 times 100 is 15,000 X. So remember, when X is 2, for example, that really means 200 phones were sold. And so you plug in 2 here for X and you multiply that by 15,000 and you get $30,000 would be your revenue if in fact you sold 200 phones at $150 each. Your cost is a combination of what's called a fixed cost, which is this 20,000. That's, for example, could be the cost of the building in which you are running your business. The monthly costs that have nothing to do with how many phones you actually sell. It's fixed. It's 20,000 per month, plus you have to pay for constructing the phones that you plan to sell, and that costs $30 per phone, and again multiplied by 100x phones. The units here will be dollars. Ultimately, it's going to be 20,000 plus 3,000x. This is our cost function. Now, profit is how much money you have after the revenue and the expenses have been taken into account. So it's how much money you bring in, which is your revenue, but then you have to subtract from that your costs, so minus the cost function. So our revenue is 15,000x, this is measured in dollars, minus cost, make sure you put cost in parentheses. It's 20,000 plus 3,000x. Distribute the negative across here, so you have 15,000x minus 20,000 minus 3,000x. So I can combine the x terms and get 12,000x, and then minus the 20,000. And this is measured in dollars as well. All right, use technology to graph the profit function and find the break-even point. I've already programmed into Desmos a lot of the equations and functions I plan to graph for this lecture. So I'll reveal them as I use them. But I have a revenue curve here, and our scale needs to be changed dramatically since the revenue is 15,000x. So we expect a very, very steep line. So I'm going to change my y scale until I start seeing thousands. Now you can see what that looks like. Let me spread out the x-axis a little bit. And here's our revenue curve. Different points along this curve indicate if x is 2.2, that really means you sold 220 phones, and then your revenue would be the second number, $33,000. So this is our revenue function. Our cost function is this blue one. Where they intersect is called the break-even point. So this point that's highlighted right here suggests that if you sell 167 roughly phones, we can expect to break even, because your revenue and your costs will be equal at $25,000. And if your costs and your revenue are equal, that means your net gain is 0. Now if I graph the profit function, you'll notice something. The break-even point, look at the x-coordinate and compare it to the x-intercept x-coordinate of the profit function. They are the same. So where the profit is equal to 0 is also your break-even point. Now naturally you want your profit to be positive, meaning that you have more revenue than you have costs to have a viable business. The other intercept of our profit function is at negative 20,000. That suggests that if you made 0 phones and sold 0 phones in a month, that you would be in debt 20,000. That's because your fixed cost for the month was 20,000. So you have to make and sell phones in order to get yourself out of debt. And it requires you to make 167 phones roughly in a month and sell them in order to break even. And naturally you'd want to make and sell more than that in order to have positive profits. I'll put our x-axis and our vertical axis, which is dollars. Let's go with a scale, put the negative 20,000 right here. So this is 1 point on our line. And let's say that this is x equals 2 over here, x equals 1 is there. The 1.6 repeating is going to be our actual intercept. So 1 2/3 is approximately right there, and then our profit function is a line going through those 2 points. Now that's going to be 5/3 comma 0 will be that point right there. The 5/3, if you recall, was the 1 2/3. It's equal to 1.6 repeating, so 666 forever, which is approximately 1.67, which translates into approximately 167 phones. This is what we mean by the break-even point. The profit will be 0 if you make and sell 167 phones. Will be near 0, I should say. This is approximate because we did a little bit of rounding right here. Now, to have solved this by hand, you would simply take the profit function, which is 12,000 x minus 20,000, and change the profit to 0 and solve for x. So add 20,000 to this side, and then divide, and we get x is equal to 20,000. I'll put 20k divided by 12k. The thousands cancel. We get 20 over 12. Each of those is divisible by 4, so we get 5/3, 100 phones. Okay, let's go to the next task. Express the area and circumference of a circle as functions of its radius. If you have a circle and then it has a center, the distance from the center to any point on the circle would be its radius, and it remains constant. Area of a circle is pi times the radius squared. So you can call this a function of its radius. So if you want to go more formal notation with function, you say a of r. A of r equals pi r squared. Now the circumference of a circle. We'll use c for circumference. We'll write it as a function of r, and it's 2 pi r. Now suppose the circumference of a circle is x meters long. Express the area of the circle as a function of x. We begin with the circumference equals 2 pi r, change the circumference to x, and then solve this equation for what the radius would have to be. It's x divided by 2 pi. And the area is pi r squared. But I'm going to replace the r with x divided by 2 pi. Now I can simplify that by squaring top and bottom, so it's pi times x squared over 4 pi squared. And when you square 2 pi, make sure you square the 2 and the pi both. This pi and one of these pi's here is going to cancel, so I can get that the area as a function of x is equal to x squared over 4 pi. Now we're supposed to graph this area function a of x and interpret the meaning of a of 4. And here we have our area curve. Now x represented the circumference of the circle. So we wouldn't want x to be anything smaller than 0. Like a negative circumference doesn't make sense in this context. So let's go with 0 as the smallest possible circumference, and then we can only go up from there. We want the x-axis to be horizontal, and the vertical will be an area axis. So we're graphing a against x. If you can tell me its circumference, I can tell you its area using this function. So right around when we get to 7, we're really close to the point 0.74. Not quite there, but and the one I'm doing by hand doesn't have to be exact. Now let's interpret the meaning of a of 4. A of 4 would be right in here somewhere. It'd be 4 comma a of 4. And according to our function over here, we just have to plug 4 into the capital A sub 1 function. So capital A sub 1, parentheses, put a 4 there, and it does the calculation for us. Plug in 4 for x, you get 4 squared over 4 pi. We can cancel some 4's though, so it's really just 4 over pi. And that decimal is approximately what we're seeing here, this 1.27 we'll say. And then what unit will we put on this? Well, this is an area of a circle. So it's going to be a square unit, and we were working with meters. So this is square meters. And the 4 that we plugged in was the circumference, and that would be measured in meters. So what this is telling us is that when you have a circle whose circumference is 4 meters, then the area of that circle will be 1.27 square meters. And every single point on this function relates the circumference of the circle, which is x, to the area of the circle, which is the output, or you can say is the second coordinate. Let's go to the next example. In the image below, the point xy, so this point right here, is a first quadrant point on the curve of the indicated function. So this function here is giving us the curve that you see right here. And so we have some point on that curve, and then from that point we're going to construct this first quadrant rectangle that's shaded in gray. And our goal is to express the area of the shaded rectangle as a function of x and give its domain. I can plug 2 in for here and see what the y-coordinate would be. You would find the y-coordinate by plugging 2 into this function f. 42/25 is the output I'm getting. Anyway, let's pretend like we had a simpler y-coordinate. If this was the point 2, 1, then that would tell us that this length here is 2 and this height is 1. So that would give us the length and width of this rectangle. So the x and y coordinates give you the length and width. And the y-coordinate, of course, is equal to this function. So if we want to say the area of the gray rectangle, it would be simply x times y. x times y, length times width, would give us the area of that rectangle. But if we want this to be a function of x only, we want to replace the y with that function, because that's the rule that you use to calculate the y-coordinate for every single point along that curve. So we change the y to 2 minus 2/25 of x squared. Now I'm going to go ahead and put the of x notation here. So this is area of x, and distribute this x across the parentheses. That gives us 2x minus 2/25 x cubed. And we want to give its domain. So we want to say, what values of x do we even have a first quadrant rectangle? So we don't want the point to be over here. The y-axis technically isn't in the first quadrant. We want to be somewhere on this portion of the curve, but not on the axes, which means we have to figure out the x value where this function intersects the x-axis. That's going to be done by taking this function right here and setting it equal to 0 and solving for x. 0 is equal to 2 minus 2/25 of x squared. I'm going to add the fraction to both sides, so we have 2/25 of x squared equals 2. I'm going to multiply by 25, divide by 2, and we get x squared is equal to 25, so x could be plus or minus 5, suggesting that there's another intercept somewhere over there at minus 5, but we only care about the one that's over here below the first quadrant. So this tells us that we want to keep positive 5 as that point of intersection. Again, to keep this point in the first quadrant, we need x to vary between 0 and 5. X itself has to be somewhere in this window right here. That'll guarantee when you plug it into the function, we get a point somewhere up here in the first quadrant. So our domain of this function will be x must be more than 0 but less than 5. Now graph the area function using technology and determine the dimensions of the rectangle that has maximum area. So I've graphed the function here that's red. And so you can see as this point varies, we get different kinds of rectangles. Now the question is, where should I put this red point? Where should it be exactly so that the area is maximized? Now if you get it too close to the y-axis, our rectangle all but shrinks to nothing. So the area of the rectangle is 0 effectively. If you get too far this way, the same thing happens. You get essentially a 0 area rectangle. So that suggests that somewhere in the middle is going to be where our area is largest. And the way to resolve this is to actually graph this function here that we just found. 2x minus 2/25 of x cubed. You get this curve. I'm going to crop it. I only want it to be visible for 0 to 5. Curly brackets, 0 less than x less than 5. So there's our area function as a function of x. Let me hide some of these other things that we're seeing here. So this area function, if you click on it, Desmos will automatically find its highest point. This is telling us that the x should be 2.887 and that the resulting area of the purple rectangle will be 3.849 square units. Let me put the other images back into play here. And as I move this red point around on this curve, we get different areas of the purple rectangle. Well, the purple curve is telling us what those areas are as I vary the x-coordinate. So if I pause right there, this is suggesting that if the red point has an x-coordinate of 2.19, then the resulting purple rectangle will have an area of 3.54. Now, of course, we wanted this to be maximized. So we want to park x where we see an obvious highest point on the purple curve. So around 2.86. I'm going to hide these images and just simply click now on the purple curve, and Desmos finds that maximum for you. 2.887, that's a rounded number most likely, and 3.849. But rounded to the nearest thousandth, this is the location of the maximum point. Okay, so plotting this point, and we had a function that went up to there as a maximum and then came back down to 0. It did have two intercepts, and determine the dimensions of the rectangle that has maximum area. So this is the x-coordinate. This is the, if you will, we can call this the length of the rectangle, and if you want to call the y the width. So the length of the rectangle is 2.887, and we didn't put units on this, so whatever these units are, this is length and this is units. This number here is an area, not the width. Be careful about that. And it would be square units. These two numbers here don't answer the question. It gives us part of the answer to the question. The question is to find the dimensions of the rectangle that has maximum area. Well, we found the length, but we got to find the width. So we got to find the y. So I got to take this number, 2.887, to get the width, I got to plug it into the function f of x. You have to be careful that the y-coordinate in this image here is not the same interpretation as the y-coordinate in this image here. It's better to think of y as a width of a rectangle, x is a length of a rectangle, and then the output of this function is an area of that rectangle. So the width will be found by doing f of 2.887, which is approximately, do that using the technology, and say that f of 2.887. And we get 1.333 approximately. and this would be measured also in units. And go to the next one. Find the point on the curve y equals square root of x that is closest to the point 4, -1. What is this minimum distance? The way we're going to do this is I have an arbitrary point on the curve y equals square root of x. And then I have a point here at 4, -1. Now this point here, you want to be able to imagine it moving. And at each time you stop it, you measure the distance from that point to the point 4, -1. And keep in mind that this one is arbitrarily located. So you have to imagine that point moving around the curve, and consequently this diagonal line would be shifting. And it's going to have different lengths. We want to figure out the function that tells us that length. And we want it to be a function of x. We'll use d for distance, and x will be the x-coordinate of this point right here. In order to do this, we're going to do the Pythagorean theorem. Going to actually imagine a right triangle sitting right here, determine what its two legs are, and then use Pythagorean theorem to get the d. So let's just call this d for now. When you want to find the horizontal length, you do this coordinate minus this coordinate. You do x coordinate minus x coordinate. So this would be 4 minus x. To find the vertical distance between 2 points, you do coordinate minus coordinate, y minus -1 or y plus 1. So the Pythagorean theorem gives us that 4 minus x squared plus the other leg, which is y plus 1 squared, should be equal to d squared. This is the Pythagorean theorem. So if I want to solve for d, I would get d is equal to, and then the square root of all this stuff. Be careful you don't cancel the squares. This is a common mistake that some students make with squares. For example, sometimes students will want to say, oh, that's just the same thing as 3 plus 4, and they get 7. So they say the square root and the squares cancel. But in reality, what's 3 squared? It's 9. What's 4 squared? It's 16. Add those together first, you get 25. Then take the square root, you should get 5. So we have an inconsistency here. So if you have a square root of a plus b, you cannot do square root of a plus square root of b. However, you have a square root of a product, you can do square root of the factors. So this is good, this is bad. So this expression that we have cannot be simplified. But currently, d is expressed as a function of two variables, x and y. But this y right here is the same thing as square root of x. So what we're going to do now is change the y in our expression, and then we have d, distance between the 2 points, as a function of x only. So we get the square root of 4 minus x, that's being squared, plus, and then the y, change it to radical x, plus 1, and that's being squared. And there is our distance function as a function of x. Use technology to graph the distance function and resolve the task. Well, the task is we are trying to find the point that is closest to 4, -1, the point that's on the curve, and we want to find out what that minimum distance is. Okay, so here I have a draggable point on the curve y equals square root of x. As the point moves, the green line segment shrinks. We actually are closer to the point 4, -1, but after a certain while, the green line segment's going to grow in length again. If I kept going, that green line segment would just get longer and longer and longer. Just by sort of eyeballing it and seeing when the green shrinks and when it grows, it looks like it's somewhere in this area to me. So roughly in this area here, 3.13, 1.769, I'm expecting to have a minimum distance. Now I'm going to graph the distance function that we just found. Bear in mind, you're going to see some differences in how this is written and what you saw over there. If you do 4 minus x and then you square that, it's the same thing as doing x minus 4 and then squaring it. When you square a difference, it doesn't matter what order you do the difference in. For example, 5 minus 2 squared, compare that to 2 minus 5 squared. In both cases, you're going to get 9. Right? 5 minus 2 will be 3. 3 squared is 9. 2 minus 5 will be the opposite, -3, but because of the square, it won't matter. You're going to get 9 out of this. So there's some freedom here in how you write this distance function. The fact that this is addition right here means that you could swap these two expressions. So there's lots of freedom here as well. This square root of x, I'm calling it g of x in my programming over here. But g of x, as you see described up in orange, was defined to be square root of x. So anyway, I've graphed my distance function. It's in green. If you click on the green graph, it'll automatically find the lowest point for you. And it's saying 3.221. Let's park this somewhere like right here and see what this information is telling us. So look at the orange point on the orange curve. 1.37 is the x-coordinate, 1.17 is the y-coordinate. And you get that y-coordinate by doing the square root of the x-coordinate. But that orange point on the orange curve is a certain distance from the point 4, -1. And that distance is given by the second coordinate of the point on the green curve, the 3.41. So the two orange points are 3.41 units apart from each other. As I vary this and move to a different location, notice that the distance shrunk, 3.049. And we want to keep doing this until you get a minimum on the green curve, because once you go past the minimum on the green curve, go up this direction, the distances all start to grow again. So I'm going to click on the orange-green curve. That's the x-coordinate I want. So when the x-coordinate is 3.221, then the two orange points will be 2.901 units apart from each other. That's how long that green dashed line segment is. And the point on the orange curve that's closest to the orange point not on the curve, 3.221, comma, 1.795. And you get the 1.795 by doing the square root of 3.221. 3.221, comma, 2.901. And that is roughly in this area. And this minimum point tells us that, keep in mind that the first coordinate is the x, and this second coordinate should be interpreted as a distance, the distance between the point on the curve and the point 4, -1. So the point on the curve, which is y equals square root of x, closest to the point 4, -1, is the point 3.221. That's the x-coordinate. But the y-coordinate, don't put the 2.901. That's the actual minimum distance. We want to do the square root of 3.21. It's going to be the orange second coordinate you see here, this 1.795. And then the min distance is 2.901 units, whatever these units are. Okay, one more task. A box with a square base and no top must hold 50 cubic centimeters of liquid. Find the dimensions of the box that minimize the amount of material needed to make the box. Okay, so I've drawn a picture of a box with a square base and no top. You have a length, a width, and a height of a box. And we know that the volume of a box is the product of these three dimensions. The surface area, I'll do S for surface area, is the area of all the sides. There's only 5 sides of this box because it has no top. And before I take this much further, let's go ahead and now go with the fact that we have a square base. So the L and the W are the same. And I'm going to use X instead of these letters here. So if I call this X and X, let's call that little h for the height. And let's rewrite my formula for volume. It's going to be X times X, or X squared times H. Now the surface area, if you were to fold the flaps down, it would look something like this. And you would have X by X, and these would be the H's. So you want to do the area of each side, and each side is going to be the same. All 4 sides are the same because the base is a square. So we're going to have 4 xh's plus, and then the area of the base, which is x squared. And this comes from the 4 sides, and this comes from the base, all added together. Now, we know that the volume must be 50 cubic centimeters. All these lengths, by the way, x, and h, are going to be measured in centimeters, and when you multiply them, you get cubic centimeters for volume. And we know the volume has to be 50. So the volume has to be 50 cubic centimeters. I'm going to leave the units off from now on. And currently our surface area has 2 variables involved. It's x and h. We want to be able to boil this down to a function of just one variable. So I'm going to target the h for substitution. By using this volume information, we can solve this for h and replace that into the surface area function for h. So divide both sides by x squared, we get h is equal to the 50 cubic centimeters divided by x squared. Now we're going to take this and substitute it into our surface area expression. So it's 4x times h. H is 50 over x squared, and then plus another x squared. And then simplifying this expression a little bit, we have 4 times 50 is 200, and then x over x squared will just leave dividing by an x, plus x squared. This is our surface area as a function of one variable, x. So I'm going to write of x. Put this in function notation. Now as x varies, we want to be able to determine what value of x is needed so that the surface area is minimized. So now we're going to go back to Desmos, and currently I don't see anything. So just keep zooming out until you see some image. Oh, look at this. I see graph over there, and ooh, I see graph up there as well. And I'm only interested in x being positive because x stands for the length of the base. So whatever this graph is doing left of the y-axis, I really don't care about. But I do want to change my vertical scale so I can see this a little bit better. This is the portion of the graph I'm interested in seeing when x is positive. And for different choices of x, you can see I get different surface areas. Just click on the blue graph anywhere. The minimum will be highlighted, and we have this point here, 4.642, 64.633. And I'll throw a rudimentary graph in here. So here's the x-axis. This was the surface area axis, because we're graphing s against x. We're graphing that function right there. And it made a graph that did something like this. And this point right here was the point whose coordinates I just wrote down. Okay, now keep in mind then that the first coordinate here is an x-coordinate, where x is the length of the base in both dimensions, because it's square. And this is a surface area. And specifically, it's the minimum surface area, because it's the lowest point in our surface area graph. Now the instructions here were find the dimensions of the box that will minimize the amount of material needed to make the box. So we know these two. That's this first coordinate in our graph. But we got to figure out the h. That's the other dimension. And we figure it out by doing this expression. H is equal to 50 divided by 4.642 squared. And there's the corresponding h, 2.320 approximately. Okay, so let me shrink this down a little bit, put it right there, and then write my answer over here. So the amount of material needed to make the box was essentially its surface area. So we minimized the surface area, and the dimensions are, the base is 4.642 units by itself, 4.642 units. The height of the box is 2.32 units. Oh, and we actually know the units in this case. They were specified, so I can go in there and put in the correct unit. We're talking centimeters here. The volume will be 50. Like if you multiply these three numbers, you'll get the 50 cubic centimeters. And the minimum surface area is the 64.633. And this is a surface area, so it's going to be square centimeters. Okay, I think we have adequately answered this question.